Hello everyone. We will introduce about cascading spy sheets. Our team name is CSS Spy. We have four members: 박서진, 서민경, 서현우, 현지성. Each of us is responsible for analyzing, re-implementing, and testing parts of the paper's proof of concepts. Together, we focus on reproducing the experiments from the paper cascading spy sheets. We selected this paper because it reveals a new attack vector in a well-established standard, CSS. It bridges theory and practice through real-world demonstrations, proposes concrete defenses backed by experiments, and expands our understanding of web and email privacy risks. The main findings are modern CSS alone can fingerprint users accurately. Attacks extend beyond browsers to email clients, and current defenses like Tor or Brave don't stop these attacks. The technical contributions include three novel CSS fingerprinting primitives and demonstrations in restricted environments like email, root cause defenses for browsers and emails, and responsible disclosure of vulnerabilities with public artifacts. Next is detailed re-implementation plan about methodology, tools and technologies to be used, and required resources.
This experiment shows that CSS calc expressions and container queries can be used to fingerprint web browsers. The experiment is designed for Chrome, Firefox, and Tor browser. Let me explain how this works with a code example. Look at the first image on the right. This shows the calc function used in the POC. The calc function contains a complex mathematical expression. It includes exponential operations, pi constants, trigonometric functions like sine and cosine, and multiple nested calculations. This expression evaluates the different pixel values depend on the browser implementation, operating system, and CPU architecture. Now, look at the second image below. This shows how container queries use the calc result. The container's width is set using the calc expression. In this example, the width is 0 pixels on Ubuntu 22.04 LTS and 1.84375 pixels on Windows 11. The container queries then check this width. If the width equals 0 pixels, the Ubuntu specific styling is applied, showing orange color. If the width equals 1.84375 pixels, the Windows specific styling is applied, showing blue color. This demonstrates how subtle differences in calc evaluation can fingerprint the operating system without any JavaScript. Let me explain the tools and resources for this experiment. We test on two operating systems, Windows 11 and Ubuntu 22.04 LTS. We use three browsers, Chrome, Firefox, and Tor browser. The dataset consists of three HTML files, POC Chrome HTML, POC Firefox HTML, and POC Tor HTML. Now I will explain the methodology. First, in the Windows 11 environment, open POC Chrome HTML, POC Firefox HTML, and POC Tor HTML. Verify that the result text shows Windows 11 in each browser. Second, in the Ubuntu 22.04 LTS environment, open the same three HTML files. Verify that the result text shows Ubuntu 22.04 LTS in each browser. Finally, record all results. Experiment shows that popular browser extensions can be detected using only CSS. The experiment is designed for Google Chrome. Now, let's look at the tools and resources needed. The browser we use is Google Chrome. The dataset consists of 9 HTML files. These files are located in the POC's extensions path. Now, let's move to the methodology. We open each HTML file on Google Chrome twice. First, without the extension installed, then with the extension installed and enabled. The procedure is as follows. Simply visit each HTML file into stage. Once with the extension, once without the extension. The success metric is visual difference. The experiment is successful if any visual change appears. This could be color, text, or layout changes. The experiment shows we can identify translations performed by Google Translate in Chrome. The core principle is that different languages have unique glyph rendering widths, which container queries can measure to identify the translation language. Let me explain the tools and resources for this experiment. We use Chrome browser version 126. The environment is macOS Sonoma 14.5 running in a virtual machine. The dataset is a single HTML file, POC Chrome Translator HTML. Now I will explain methodology. First, open the POC Chrome Translator HTML file in Google Chrome. Second, use Google Translate to change the page language. Translate it to German, then translate it to Catalan. The success metric is as follows. When translating to German, the text German should appear. When translating to Catalan, the text Catalan should appear.
Experiment 6 is about email client fingerprinting POC. The purpose of this experiment is to demonstrate that state-of-the-art CSS-based fingerprinting can be applied to email clients. For this, we'll use a set of proof-of-concept emails that demonstrates the visibility of the techniques in some email clients. The methodology is as follows. First, set appropriate email client OS combinations and transfer prepared email files to each combination. Second, visit the provided EML files with the respective email client and OS combination. Each EML file contains calc expression or container query or media query. Lastly, compare the results text between the email client and OS combinations. We can see different text according to the email client and OS combinations. Tools and technologies to be used as follows. Oracle VirtualBox as virtual machine, Windows 11 and Ubuntu 22.04 LTS as OS, Thunderbird 150.15.12.2 and Apple iCloud Mail as email client, Google Chrome 126 as browser, and MS Office as additional application. Required resources are datasets, which are email files that contain calc expression or container query or media query. Experiment 7 is about extension mitigation. The purpose of this experiment is to evaluate the extension-based mitigation that preload all resources that are referenced in the CSS of a site. Methodology is as follows. First, crawl 50 sites from Firefox without extensions. Second, crawl 50 sites from Firefox with extensions. The extension checks for occurrences of the URL, image, or image set functions in external style sheets, inline styles, and style attributes. For every identified URL, the extension injects a hidden image into the DOM and that fetches the identified resource. Every remote resource is requested unconditionally, and later requests are served from the HTTP cache of the browser. Lastly, compare the network traffic statistics and calculate overhead of crawling with extensions. If the crawl is successful, the overhead is less than 30% and there is no overhead greater than 50%. Tools and technologies to be used in this experiment is as follows. Oracle VirtualBox as virtual machine, Windows 11 as OS, Firefox as browser engine, Python 3 version as language, Playwright 1.44.0 as automation tool, NumPy 2.0.0 as library for statistics. Required resources are crawling targets, which are Tronco top 50 sites.
Next experiment is about email mitigation. Purpose of the experiment is inlining remote component so that we can mitigate the fingerprinting. But inlined email files have more space because of base 64 encoding. Methodologies are as follows. First, we export a set of emails from one of our inboxes. Second, run the Python script on the exported files. The script will fetch all remote resources contained in the files and inline them as data URLs. The output will be to a new folder. Finally, compare the sizes of the initial and the output folder. Then we can know the space overhead of inlined files compared to the original files. These two codes convert remote components of email HTML into data URL. First, the left code convert remote URL into data URL. It takes files from URL, encodes by base 64, then it can generate data URL. The right code convert CSS images into the data URL. It takes image source and background image, then convert them into the data URL. Tools and technologies are as follows. First language is Python 3.12, and email client is Thunderbird and Outlook. Analysis tool is Shell Utilities, and OS is Windows 11 and GitHub URL. Required resources also as follows. First, we need EML files for experiment. Second, we need extra space for inlining, because compared to the given EML files, inlined files takes more space. This is the timeline for the re-implementation. Thank you for listening to our presentation.